Effect of shear wall area on seismic behavior of multistoried building with soft story at ground floor. Abstract. The trend towards progressively taller structures has demanded a shift from the traditional strength-based design approach of buildings, to a focus on constraining the overall motion of the structure. Nowadays reinforced concrete, RC, wall frame buildings are widely recommended for urban construction in areas which are prone to earthquake. Construction of shear walls imparts a large stiffness to the lateral force resisting system of the RC building. Proper detailing of shear walls can also lead to ductile behavior of such structures during strong earthquake shaking. One of the main parameters influencing the seismic behavior of shear wall frame buildings is the shear wall area ratio, and shear wall area ratio need to be studied. Thus an analytical study is performed to evaluate the effect of shear wall area to floor area ratio, SWA/FA, on the seismic behavior of multistoried RC structures with soft story at ground floor. For this purpose, 9 building models that have 5, 9, and 12 stories with various SWA/FA in both directions are generated. Then, the behavior of these building models under earthquake loading is examined by carrying out response spectrum analysis and linear static analysis using structural analysis software Etabs. Response spectrum analysis and linear static both are carried out according to seismic code IS 1893:2002. Keywords: reinforced concrete, shear wall, response spectrum, linear static analysis, earthquake resistant structures. Introduction. Over the few decades, shear walls are widely used in countries especially where chances of earthquake are very high. Shear walls are designed not only to resist gravity loads but also withstand the overturning moments as well as shear forces. The major factors for inclusion of shear walls are ability to minimize lateral drifts, interstory displacement and excellent performance in past earthquake record. They have very large and plane stiffness that limit the amount of lateral displacement of the building under lateral loadings. Shear walls are intended to behave elastically during moderate or low seismic loading to prevent non-structural damage in the building. However, it is expected that the walls will be exposed to inelastic deformation during less or frequent earthquakes. Thus, shear walls must be designed to withstand forces that cause inelastic deformations while maintaining their ability to carry load and dissipate energy. Structural and non-structural damage is expected during severe earthquakes. However, collapse prevention and life safety is the main concern in the design. To minimize loss after earthquakes, the experimental and analytical studies on seismic design approaches encourage use of shear walls for earthquake-resistant design. The effect of shear wall ratio on structural vulnerability could be evaluated by the variation of different parameters such as roof or interstory drift with increasing shear wall ratio. 1.2 Definition of soft story. The main difference between a soft story and a weak story is that, while a soft story is classified based on stiffness or simply the relative resistance to lateral deformation or story drift, and the weak story qualifies on the basis of strength in terms of force resistance, statics, or energy capacity, dynamics. 1.1 Story drift. The drift in a story is computed as difference of deflection of the floor at the top and bottom of the story under consideration. The total drift in any story is the sum of shear deformation of that story, axial deformation of floor system, overall flexure of the building and foundation rotation. 1.1.1 Behavior of shear wall. Shear walls are the main vertical structural elements with a dual role of resisting both the gravity and lateral loads. Shear wall constructed in the high-rise buildings generally behave as vertical cantilever beam with their strength controlled by flexure as shown in Fig. 1.3. 1.2 Aims and objectives of the study. The aims and objective of the present study is to study the relationship between SWA/FA % and base shear for all 9 models. To study the effect of SWA/FA % on roof displacement for all 9 models, and to study the effect of SWA/FA % on story displacement for all 9 mod. 5-story model. It can be observed that for 5-story building model, the difference in roof displacement is not much significant, especially for 0.93%, x, 0.54%, y, SWA/FA %. A significant decrease in roof displacement can be observed with SWA/FA % equals 1.2%, x, 0.7%, y, which indicates that at least 1.2%, x, 0.7%, y, of shear wall ratio should be used in design. In case of 9 and 12-story building model, similar pattern can be observed in roof displacement. It was observed that as the height increases the displacements are also increases, but by increasing the SWA/FA % the displacement's values decreases. In case 5-story building model, when SWA/FA % equals 0.93%, x, 0.54%, y, maximum displacement are observed as expected. After this point, the decrease in displacement is relatively lower between 1.2%, 0.7%, y, and 1.47%, x, 0.85%, y, shear wall ratios. Literature review. 2.1 Introduction. In this chapter we will discuss the different studies which were performed in past in regards to the seismic analysis of multistoried buildings with different shear wall ratios. The discussion comprises of 10 previous works which were conducted to show the effect of shear wall ratio on different types of structure and recorded the response plots under some previous earthquake worldwide. 2.2 Literature reviews. Fintel, M3, 1995, Performance of buildings with shear walls in earthquakes of the last 30 years. In historical earthquakes, reinforced concrete structural walls showed to be very effective in preventing collapse and damage of buildings under strong and frequent events respectively. Hassan and Sozan 4, 1997, Seismic Vulnerability Assessment of Low-rise buildings in regions with infrequent earthquakes. A simplified method proposed which enables ranking an inventory of low-rise, up to 5 stories, monolithic RC buildings based on their seismic vulnerability level from low to high by using column and wall indexes. This method requires only structural dimensions as the input and is based on effective wall and column indexes plotted in a 2-dimensional form. Ersoy, 1999, and Tekel 5, 2006, Seismic Strengthening of RC Structures with Exterior Shear Walls in Earthquake-Resistant Design. When a dual system is used, the general approach is using a shear wall area to floor area ratio of about 1.0% as a rule of thumb. Ozan Soidas 9, 2009, Evaluation of shear wall indexes for reinforced concrete buildings. Earthquake ground motions induce lateral forces that cause lateral deformations on both structural and non-structural components of a building. Methodology. 3.1 Introduction. Earthquake and its occurrence and measurements, its vibration effect and structural response have been continuously studied for many years in earthquake history and thoroughly documented in literature. Since then the structural engineers have tried hard to examine the procedure, with an aim to counter the complex dynamic effect of seismically induced forces in structures, for designing of earthquake-resistant structures in a refined and easy manner. This re-examination and continuous effort has resulted in several revisions of Indian Standard, 1893, 1962, 1966, 1970, 1975, 1984, and 2002, Code of Practice on the Criteria for Earthquake-Resistant Design of Structures by the Bureau of Indian Standards, BIS, New Delhi. The structural engineers must understand the basic design criteria and procedures for determining the lateral forces. Various approaches to seismic analysis have been developed to determine the lateral forces, ranging from purely linear elastic to nonlinear inelastic analysis. 3.2 Methods of seismic analysis. Seismic analysis is done on structural model to determine the forces induced in the structure due to earthquake. The analysis process can be categorized on the basis of three factors: the type of the externally applied loads, the behavior of structure/or structural materials, and the type of structural model selected. Based on the type of external action and behavior of structure, the analysis can be further classified as linear static analysis, linear dynamic analysis, nonlinear static analysis, or nonlinear dynamic analysis. Vescos and Anagnostolos, 1997. Linear static analysis or equivalent static analysis can only be used for regular structures with limited height. Linear dynamic analysis can be performed in two ways, either by mode superposition method or response spectrum method and elastic time history method. This analysis will produce the effect of the higher modes of vibration and the actual distribution of forces in the elastic range in a better way. Case study. 4.1 Introduction. Most building codes prescribe the method of analysis based on whether the building is regular or irregular. Almost all the codes suggest the use of static analysis for symmetric and selected class of regular buildings. For buildings with irregular configurations, the codes suggest the use of dynamic analysis procedures such as response spectrum method or time history analysis. In the present study, lateral load analysis is performed on 12 buildings models that have 5, 8 and 12 stories with the same plans, but different shear wall area ratios are generated for the application of response spectrum and linear static analysis. The shear wall area ratio is determined by dividing the total shear wall area in one principal direction to the plan area of the ground floor. A/AP. 4.3 Description of the building models. Design data. Material properties. Results and discussion. 5.1 Introduction. In this chapter, the results of the 5, 9, and 12-story building models are presented and discussed in detail. The result includes of all building models which are computed using the response spectrum analysis and linear static analysis. The analysis of the different building models is performed by using Etabs analysis package. The results of fundamental natural period of vibration, relationship between shear wall area and base shear, relationship between shear wall area and roof displacement and story displacement for the different building models for each of the above analysis are presented and compared. An effort has been made to study the effect of shear wall area to floor area ratio by considering ground floor as soft story in the analysis.